Okay, I think I'm live on Twitch, hopefully. That seems like the thing to do. And I am recording once again. And let me kick off things in here. Okay. Hello, everyone. Welcome to yet another day. Another day, another something. Whoops. I was going to have a bit of a drink. Okay. So I'd like to thank everyone who has so far participated in my sort of anonymous, not sort of anonymous, but absolutely anonymous. I have no idea who is replying, and everything is totally through Google, so I wouldn't know where to even begin to look to try to figure out who is responding to what. But so far, people have been responding, and that's a good thing. Basically, for those of you who have no idea what I'm talking about, there is a link over on Discord in the general channel to sort of a, let's call it a just status check survey, so that if anyone wants to express any issues with regards to kind of how their semester is going, how they're dealing with being remote, how they're just feeling in general with regards to the whole pandemic and politics in the world and all that kind of great stuff. It's just an opportunity to kind of clear the air, make your voice heard, and so on. And I'm going to be sort of compiling, coalescing that into something to share with the dean. She has asked that or that everyone, there's lots of people doing this in kind of different ways. You may be getting some of this from other classes as well. Just basically, kind of coalescing that into something that we can use to kind of see how people are doing and see if we need to adjust and so on. Yeah, a couple of things. It's challenging. I think for most of you in this class, you tend to be sort of on the upper class side, so you're a little bit more familiar with independent work and so on. So far, I'm hoping that that's all in there as well, with regards to freshmen, sophomores, and so on, who aren't quite as used to dealing with independent stuff, as working on their own, working remotely, working with groups. It's a little bit more challenging. But anyway, I'm just biding a little bit of time before I dive into today's lecture. I have not gone through everything. Hopefully, everyone has submitted their project 1. I haven't checked it all. It was due last night at midnight officially. So if you haven't, go ahead and check it in. Rolling submissions on that one at this point. So we'll get that out of the way and we'll get back on track and everything will be great. So that's that. Now let's see. Let's see. Morale is probably going to be extremely low considering, yeah, there was a few people who had mentioned that, and the arch is pretty brutal. I have to admit, where I stand on it, I mean, that's my opinion, of course. I can see the value in it. I certainly do see the value in internships and co-ops and that sort of thing, and trying to make that them more accessible and available and so on. I'm not sure that the arch was necessarily the absolutely only way to do it, and yeah, I can only imagine. The thing, though, one thing to bear in mind is sooner or later, work is year-round, so it's kind of bad news all around. But anyway, that's a whole another here and there. Yeah, it's kind of weird. The first summer you're out of school entirely, and you're suddenly like, oh, I have to just keep going. There is no summer vacation anymore. Actually, for me, I taught over the summer. I've always worked over the summer. So anyway, neither here nor there. But if you do have any issues, please do bring them up. I'm going to do my best to kind of elevate them to however I can. DiffyQ has been quite the cluster. Ooh, that's sorry to hear. That's kind of an important class. Yeah, I'd imagine all of the larger classes especially are tricky because getting sort of one-on-one is boy, that's rough. That's why hopefully I'm going to keep going forward with the check-ins and so on. So which is one reason why I should probably barrel along and move right on. So, where do you submit project? The submission was our check-in. That is true normally, but what I'm going to do is go ahead and submit it. From now on, it's going to always be where there is going to be a submission point on LMS because I'm going to need to post a grade anyway. So I'm going to make that available on LMS, and this way that everyone will submit in sync with one another. So I'll talk about your project submissions, if I can get as quickly as I can get to them and get them graded and kind of put stuff out there. But then we can have discussions about them during the check-ins. So I'm going to decouple the check-ins and the projects a little bit. I think that's, out of fairness and so on. Continuing really, I just really want to have that time with the check-ins to make sure that, you really can kind of demonstrate what you did, talk about what you did, and show your understanding, particularly when the projects get a little bit more complex and so on. I didn't want to do a kind of a formal, kind of crazy one of these online final exams. So the check-ins are kind of the way to kind of step back from doing exams. We'll think of it that way. They're sort of, anyway. All my, let's see, all of my HASC courses have been amazing. Oh, well, that's good. Hopefully, well, this is technically a HASC course, but it certainly veers a bit towards more towards comp sci and computer science and math just a bit. But anyway, you're all doing a great job of distracting me from where I should go. So, but it's good stuff. Continue if you do want to submit anything on the in that survey, or if you do want to reach out to me through just direct messaging. I'm always around to kind of try to field these things. One thing to bear in mind, not saying that's any excuses or whatever, but the whole world is adjusting to teaching remotely and so on. We've actually had far more students taking Game Dev 1 this semester than we planned on, and even more in Intro to Game. Okay, enough distraction. Right. Let's talk about computer graphics. So we are on to chapter 4. So we've done chapter 3. We all have a basic understanding of matrices, kind of the way they work, that we have this model, view, projection combination of matrices because we want the model's orientation or the shape of the model, the geometry of the model, which is then transformed into the world somehow using the model's worldview. And then there is a projection into what would be an orientation to reflect where the camera relationship to the geometry as well. Remember, it's not so much that there is a camera object, but that we are rendering things, orienting them, transforming and deforming them as if they were viewed by a camera. So it's that transformation process that ultimately makes it looks as if they're being projected to a camera. So ultimately, the camera, just like in Futurama, what they said is, it's not the ship that's moving, it's not the camera that's moving, it's everything that's moving around the camera, right? So we render the world as if the camera was viewing it, as opposed to actually going through some sort of creating a view and then, okay, get the idea now. So that's where we're at. We have those basic transformations. We talked a little bit about, we can look at rotation matrices pretty much in terms of Euler angles. If you are interested in more details on quaternions and the whole axis angle approach to things, we're going to touch on that a little bit here and there, and there's a lot of resources I've been posting on that, specifically in the quaternions channel over on the site as well. I just realized I don't have headphones on today, which is on me. Let me double check to see where. All right, so if you were to talk, I probably would hear you. Just come through my speakers. All right, there we go. Have that. If you have any questions, just shout them out. That's all good. So, all right. So, does everyone have, we have a reasonable understanding now of the use of matrices, the use of rotations, the matrices to represent translations, transformations, rotations, and so on. And then we can have this sort of hierarchy of transformations that allow us to do things in terms of model space, world space, and the camera's view of the world. Now, as we get into more complex scenes, obviously we may have multiple models within that scene, right? And ultimately, you may even have multiple ways of rendering the scene, depending if you have, picture in picture. If you have like a camera looking at, or multiple cameras of the same scene, you might be rendering multiple times according to different viewpoints and so on, that sort of thing. So we start to get into this discussion, and we need to basically somehow structure things in a way that's a bit more complex than just one set of matrices and one set of transformations and one set of geometries, right? That's where the whole OpenGL pipeline and sort of data management kind of come in. There's been a bunch of good questions coming in, specifically like, well, in looking at the programs, hopefully you've, I'll do a quick poll here. Programs yet. Okay. So not too many. All right. Well, some of this will be new. Some of this will be review. I'm going to show one particular program that is based on Chapter 4, but is entirely different, based on some questions I got. Basically, OpenGL is a complex interface. It's a complex API. There's no one way to do things, and sometimes it does sort of come down to style and efficiency and how you want to approach it. So we'll talk a little bit about that, especially kind of going forward. But like I said, chapters 4, chapters 5, very, very fundamental stuff, because they are, again, dealing with, getting the whole vertex attribute and buffer objects kind of under our belt, getting sort of the basic geometry and transformations under our belt. And then 5, we're going to talk about loading textures and getting that to happen. So that's going to be pretty fundamental stuff. And we'll touch on a little bit of, answering questions and so on that kind of come up that seem to make sense. Okay. So not too many people have seen these yet. So hopefully things will be a little familiar. We'll look at a little bit of the text ones and talk about the homework ones, or the exercises. Now, at the end, I was looking through some things, and I had thought initially that the exercises were always marked exercise at the end of the chapter. Some of them are marked project, and they're not really project depth. I have a lot of faith in the ability of you all taking this class, and I think some of the things you should actually look through, both the exercises, the projects, and the research suggestions at the end of each chapter, and choose which ones kind of interest you, and choose at least one, preferably 2 of the exercises, projects, research things to talk about, at the end of the chapter. Those are the things that are going to come up as foundations for your projects, and also we're going to be talking about them in the check-ins. So make sure you should be doing that. Now, I think it's chapter 4 specifically that I think they shows them more as projects as opposed to exercises, but they're just words. All right. So the pipeline, and let's see if I can do this correctly now. I'm trying to get, yes, okay, here we go. Now, we have hopefully seen now, we're making the transition from our brain-dead vector shaders, vertex shaders of kind of chapter 2, where we had basically the geometry hard-coded into the vertex shader, and it would use some hard-coded position that the vertex shader would know about, and just based on the index, because every time you're rendering a vertex, it gives you the index of the vertex that it thinks, if you're rendering 36 vertices. So it's going to give you an index, 0, 1, 2, 3, 4, 5, 6, kind of step through all those. And then it was making a decision to use a hard-coded address that the vertex shader knew about. It's not a very efficient way to do it. What happens when you have more complex models? What if you want to load models from disk? What if you want to, manipulate models as they go? So we're going to put that aside, and we should really be looking now at those vertex attributes and vertex buffer objects. We've talked about those in previous lectures, so hopefully this shouldn't all be hitting you cold now. These should make more sense. All right. So we do need, of course, to send, in this case, we want to send data from the C++, the CPU program, to the shader programs. You have 2 ways of doing that. Most of you have seen already. You have a buffer, which is a vertex attribute, a buffer to a set of vertex attributes. And you also have the ability to send uniform variables from your C++ program to your shaders as well, right? So uniform variables are in contrast with the vertex attributes, meaning vertex attributes, you have one set of data per vertex, whereas uniform variables are something that are going to be shared across a whole rendering context. When you call GL draw elements or draw array, it's going to use that same uniform variable until the next time you change it for the next batch of rendering. Okay, so in OpenGL, a buffer is called a VBO, a vertex buffer object. Now, VBOs are independent. Don't get them confused with vertex attribute objects or vertex array objects. We want to call them VAOs. So don't get your VAOs and your VBOs kind of mixed up. Generally, when you have an array or a buffer of attributes, one per vertex, that's in your vertex buffer object. When you have something that describes a way, a set of them, that description really is part of the vertex, the VAO. VAO is the head of the hierarchy, and then the VBO describes all the individual vertices inside there. Okay, so the VAO does not refer to an individual vertex, whereas each element of the VBO does. Okay, now these are two independent data structures within OpenGL, right? They're independent data structures within OpenGL, right? You don't necessarily have this VAO. Well, ultimately you're going to bind them together, but you create them and you allocate them independent of one another. Okay, so notice VBOs are declared and instantiated in the C++ OpenGL application. Okay, similarly, the VAO is set up there as well. You should have seen that in your programs. So you go through a number of steps to send object vertices to a vertex attribute, right? So during init, we create a buffer. We copy the vertices that are in our CPU program into CPU's memory. We copy them from that array into the buffer. And then at each frame, we typically, and now I'll show this is going to be different in the one program I created, but typically in display, you enable the buffer that contains the vertices, associate the buffer with a vertex attribute, enable the vertex attribute, and then use GL draw arrays to draw the object. Okay, now let's jump over and take a look at sort of a normal case of that, just to reinforce that. So we're going to look at what's the first program in chapter 4, which is this plain red cube. Okay, so I'm at 150%, so you should be able to read these pretty well. Let me know. All right, so in our example, we now have the vertex information, the vertices, the vertex positions contained within the program itself inside of this array. We have an array of 108 vertex positions, or rather, we have 108 elements. So we actually have 36 positions. Yes, that divided by 3. 36 positions, but we have, they're tuplets, right? You have an X, a Y, and a Z, of course, to go with them. So here's our positions, and inside the setup here, in our setup of the vertices, you'll see we use a VAO. We bind that vertex array, and then normally we would generate our vertex buffer objects and bind a vertex buffer object to the current vertex array. Right? So this is what you'll normally see 9 out of 10 programs you encounter on the internet. Don't the points repeat though? How are they all unique points? In this case, they you can have things non-repeating. You can explicitly have the same geometry for lots and lots of different vertices. If you want to use indexed mode, then you can reuse positions without having to dedicate the space into a specific position in this vertex buffer object. Okay, so even though there are repeating vertices potentially, you can over-specify. You can, you can have multiple vertexes that have the same position. That's totally fine. You might have vertices that have the same position but not the same color, because they might be associated with a different triangle, for example. Right? So there's situations, the normal inclination would be that, oh, okay, a vertex is a vertex is a vertex and is shared among things and so on. It wouldn't make sense to repeat it. But as you get into sort of more complex geometry and the rendering process, then you can see, hopefully, that there's more opportunities. If you have a red triangle next to a blue triangle, now somehow you've got to say, okay, these three vertices are actually blue when it comes to this point. These three vertices are red on that one, and then it knows how to render them, perhaps. Okay. So don't take anything for granted in OpenGL, because it's going to err on the side of sort of flexibility that way. All right. Ultimately, down here, if we look, you'll see that we are actually rendering 36 triangles. Right? Is that right? We have 6 sides. No. We are going through, now you've got me questioning myself. We'll step through it and it'll make perfect sense. 36 vertices, that's right. Because what it's doing is it's saying, okay, render them as triangles. Yes, by saying render as triangles, it knows to use each vertex as it goes along as part of those 3. Okay. Whew. We're getting there. So, here we go. Step back, breath. So we have our vertex array that we set up. In this case, in a lot of programs, you're going to just see a single vertex array, a single VAO. So a lot of people will change the buffers that are associated with it and change the state as their programs are running. You don't necessarily need to do that. So a VAO can basically contain all of the information about a set of vertices. Okay, so that set of vertices may be something that defines a mesh, or defines an object, or it's just in a sort of a context that you want to use over and over again, and dynamically on the fly, you may change which set of vertex attributes belong to that particular vertex array. Okay, so it is a little bit tricky. You do have this context of the vertex array that points to a bunch of vertices, but you can, on the fly, change that a lot. And that's what a lot of sample programs do. In fact, most of the samples in the book, I think, use a single vertex array, and they just change the vertex buffers underneath it, and they modify some things, which is, I'll show you in the program that I created, how I got around that or approached that a little bit differently. Okay, so let me get back on my on my train of thought here. Okay, so we have a set of vertex positions. We have a vertex array. We're saying, okay, here we're pointing to this array of vertices. This VAO is the one that refers to that. This is just an index. We say this buffer is bound to whatever the current vertex array is, which is what we just set here, right? In binding, we're saying that's the one we're using. Then we say, okay, generate buffers and bind them to the current context, the current state. Okay, so that's what's happened here. And now we're going to also make sure that the buffer data is loaded into that buffer object. And we also tell the OpenGL that this is the format of that particular buffer object, and we want to enable the attributes of that, the buffer object in this particular array. Okay, so this is our init that we talk about, or our vertex. Part of it would be done in init, setting up the vertices. So if you look up here in our init in chapter 4.1.1, it really is mostly setting up the shader, and then setting up the vertices, the vertices, and giving it sort of a standard camera location and the location of the object that we're going to be rendering, the cube. Okay, so this is the initialization there. Set up the buffer of vertices attributes, bind that to a vertex array object, enable everything. Bob's your uncle, you should be ready to render. Now, nothing's been rendered yet. Okay, the rendering actually comes down in the display function where we say, okay, use a particular renderer, use a particular combination of shaders, and then we're going to set our uniforms, which are our matrices, and then ultimately we're going to wind up, in this case, binding what buffer we want to currently use, describe it, enable that array, and then draw them. Okay, sometimes you could do this in this normal case, it's using them over and over again. We'll clear that up in fancier ways as we go. So let's get back to our slide then and see if this, so hopefully this makes a little bit more sense. Hopefully I haven't derailed things. Let's see, from current slide, there we go. All right. So just like here, we had our vertex array, we generated that, we bound that to our current context, we generated two buffers here, right? So maybe you have two sets of vertices that you want to work with. And then you want to create a vertex attribute that the vertex shader is going to use. This is saying, okay, layout, location 0 in vec3 position. This is what the shader, this is how the shader knows that there is a vector 3 in x, y, and z that is called, we're going to call it position, and it is location 0 within our set of attributes. In this case, there's only one particular set of attribute, or one attribute in there, which is just position, so it's location 0. All right. So we mentioned the step. We have to bind the buffer. So there's always this kind of setup in OpenGL, right? You bind something, then you do something with it, right? So you have sort of a context, you have your state, you know, or state of our OpenGL machine. Then you bind something to the current state, and then you do some operations, or you move something there, and then eventually things are set up, and you say draw, right? So here we have the step where we bound that buffer, then we copied information from our CPU to the GPU, basically through here, right? We had our positions, and they get sent to the currently bound buffer. And then we have some descriptive set here, right? We make that buffer active, and then we tell it how to draw, or excuse me, not how to draw, what the contents of that, how that buffer is laid out, right? So VBO is the 0th vertex attribute in the vertex shader, and it is associated with location 0. Now, again, the main thing about the vertex buffer object is that you have one per vertex. So when the vertex shader is running, each time it's going to get a different vertex. It's going to move through that array of vertices and get a different one every time. In the case of a uniform variable, you have a name declared, the type of uniform, and then it is just used over and over again. It is not changing as throughout the run of that shading step in the pipeline. All right. That's me dropping something off outside. So in order to work with that, in C++, you get a reference back. You know, okay, I can write to that uniform, and then at that point, after you've written to the uniform, then after, when the shader is ultimately called, it reads back from there. So this is this, you know, kind of dance that goes back and forth between the CPU side and the GPU side, where there's, you know, kind of, you think of them having sort of a shared, it's not really a shared address space, but, you know, the OpenGL library is kind of grabbing that data, pushing it over to the side there. Okay. In your code, you can see, okay, we are declaring a uniform variable in the shader. You declare it to be a uniform. You declare its type, and you give it a name. Okay. On the CPU side, you want to obtain a reference to the uniform, right? So for every rendering program, once you have a program that is set up with a set of shaders, you can ask it for the particular location, which is going to be an index of that particular uniform variable. We've got a question coming. Do we really need to change the uniform location every frame? Does it change? The location does not change. It actually, you can set it once, and the interesting thing is it is an index, right? So once you say to use a particular shader program, you're going to have a set of indices 0, 1, 2, 3, 4 that are going to refer to, ultimately they're the ones that are referring to the place you're going to write things. Now you don't have to change them if you don't want. It's interesting. I wrote a program that had two different shaders, and of course, in this one there's indexes 0, 1, 2, 3, and in the following one they're also 0, 1, 2, 3. So they almost look like they're referring to the same thing, except that you've got to remember you are setting the context that you're within. So they do not need to change every frame, and if you think that you are going to change a lot or there's like a big set of data, you can even do things like set up a different shader, and shaders can have independent uniforms as well as they can have independent VBOs. Or one of the cool things about VBOs is you can even share those across sort of different contexts, different vertex arrays if you want. So you can juggle things differently, but it does not need to change each frame. If your transformation matrix is not changing, you don't even have to reset it again, right? So you can just keep using it over and over and over again. So it's only if you start to animate things, move things, and so on, that it becomes important to do that. So you could just call it once, which is this mvloc equals get uniform location, and then you write the value to that location. You could do that once, and as long as it doesn't change, that program, this rendering program, will just keep using that same value. Okay, that's a good question. So this hopefully should be fairly obvious at this point. When do you use a uniform variable? It's for values that are constant across the entire object being drawn, such as the model view matrix, the projection transformation matrices. Okay, so things that aren't changing on a per vertex level is going to be sent via a uniform variable. You can have as many uniform variables as you want, and uniform variables can even be things like arrays, right? They can be vectors, they can have multiple elements. So there's flexibility in there. You can send relatively large chunks of data through there if you wanted to, if you had some compelling reason to. But remember, it is sort of a once per vertex, or excuse me, it's used, it's set once per kind of render, or once per draw of that particular context, as opposed to changing on a vertex level. So use vertex attributes when you want the values to be interpolated by the rasterizer. That's something we talked about last week as well. So the vertex attributes are being read, sort of one at a time per vertex, and then when it comes time to shade, it is even going to interpolate between those values for the sake of shading, for filling in, for that sort of thing, right? So the vertex attributes are varying, like the color that we had. That's, I think, going to be more obvious in, that's kind of weird. Let me think about that one for a moment, if I like that slide. Because like we used in this vertex shader, we had this out vec for varying color, which is, it's not a uniform. It is a variable that's shared across shaders, but I wouldn't call that necessarily a vertex array, a vertex buffer object, a vertex attribute. So I think I need to rethink that part of that slide. That seems to be. So ultimately, the vertex attributes are the things you're going to be using to set. So you are setting the values using your vertex attributes, but then the interpolation part is really part of the next part, the next step in the pipeline. So does that make sense? So in here, for example, in 4.1.2, where we're interpolating colors, once we have a position that we're reading, if we want to then interpolate across that position, we can use that in this combination of our, like in here, in our varying. I'm not liking that wording. Hopefully it becomes obvious in the examples, though. I think I might be causing more confusion the more I confuse myself. Let's continue here. All right. So we have the vertices, and ultimately the rasterization in between is happening in the fragment shader. But the fragment shader is using interpolated values that are set up kind of based on a per vertex level by the vertex shader. Okay. So here's what's here. You can picture this. Maybe this will make it easier. Okay. So the data flowing from C++ through the OpenGL, through the pipeline, vertex attributes, and uniform variables. Okay. So here's our program, the C++ OpenGL application. There are uniform variables that are sent to the shaders. You'll see here is the vertex shader. It's being sent its set of uniforms. Here's a fragment shader. Yep, it can use uniforms as well. But then the VBO is really kind of the part that starts off here moving through the pipeline. So the VBO is used by the vertex attribute, but then ultimately after the vertex shader uses it, then it is interpolating between the vertices to tell the fragment shader what to do, how to fill in between the vertices. Right? So this interpolation and rasterization step, is doing some of the work for you in terms of figuring out what is in between these vertices, and then letting the fragment shader know what to do with them, or at least giving it the hints, right? So this is the draw the red cube here in the example, and hopefully we're making some sense now, where in the application we set up the camera's position, the cube's position, then we have a perspective matrix, a view matrix, a model matrix. The model view matrix is going to be the combination of the view and the model, view and model, right? Then we have mvloc and projloc, which is going to be the indices, the location or indices in the into the shaders, so that the CPU program can tell the shaders what the MV matrix is and the projection matrix is. And we also have an aspect ratio that's computed. So sets up the shaders, sets up the values for the positions. And we walked through this before, setting up the vertices to their positions, and so on. Create the perspective matrix, build the view, model, and model view matrices. And here's where we mentioned before, get the uniform location, and this is just this index that you can then use to write that value into. And if, as Owen asked, you don't need to change them all the time. Okay. So then we bind the buffer, we enable the attribute pointer, and we enable the vertex array and draw the arrays. Okay. This has a very simple vertex shader where it does the transformations in the correct order, basically taking the position, and position is, right, we're reading from the vertex buffer here, which is why we're saying layout location 0 in vec3. So this is a vec3 that's coming in. It's going to be called position. It is being read from the 0th position of the VBO. So that's what we get here. Then we transform it according to the MV matrix, and then transform that according to the projection matrix. And the fragment shader in this case is just making it red. Okay. Whoops. So the output from that will just be a red cube positioned at 0, -2, 0, viewed from 0, 0, 8. Pretty straightforward, pretty easy. The next example uses almost literally the exact same code, but now it has a little bit of communication going on in between the vertex shader and the fragment shader, right? It's doing that through this out, right? So it declares this out vec4 and says out vec4 is varying color. Now it's not the name varying color. It's not this varying that clues us in that it is going to vary. It's just that it is an output from this vertex shader, right? So it makes this assumption that, okay, anything coming out from here is going to basically be interpolated across the positions, across the using the three locations, using the three vertices of the triangle to figure out a new location and interpolate that value depending on how close the fragment is to those three what am I saying? Those three vertices, right? Imagine you have three vertices, one's red, one's green, one's blue, and it's going to basically say, okay, you know, for this particular fragment, weight the color according to those colors, but according to the distance from any of those particular vertices, right? So you come up with a single color that is interpolated based on that, because you know that, yes, we told it we're drawing triangles, so it knows then, given three vertices, okay, it knows how to interpolate a fragment position and a value in between those, right? So this is the cube with the interpolated colors. So next, you're gonna, from there, now you will be able to animate the cube, okay? So to animate the cube, we're basically gonna, you know, doing things like changing it over time. Animation, from our point here, a lot of the examples and samples that people have actually done and implemented in their own code. Let's see, where am I? I'm doing okay, I think. You can use either the current time and sort of interpolate or move based on the current time, or some people have done things where they would just iterate, and every time through the main loop, they would increment some value and then interpolate a new value based on that. So you'd be setting the translation matrices, the angles, and so on in your main program loop, either incrementing them or looking at the actual time. And I talked to some of the people who were doing it, and I said, well, think back to working with Unity or Unreal or something, or most engines, where you would use a delta time to get things to run smoothly. So if you are doing animation in your application, you may want to figure out, you know, how much to move, how much to rotate, either depending on some sort of absolute current time, or if you're moving something relative, you want to use some sort of delta time in there as well. But that's what you're going to see in the second version. So let's take a look at that code. Just go through here. All right, so we did the interpolating colors. So we had this notion of what is going to be the tumbling cube. Let me show you that example. And let's see if I get the right. All right. So this is taking the same cube, and all we're doing is we are varying the transformation of the cube itself and then letting OpenGL render it at a new location. So it's really great. All we need to do is specify a new set of matrices, and it handles the rest. And it is properly interpolating the colors in between those points, and so on and so on. All right, so it's fairly easy to interpolate motion. Where it gets tricky is when you have more complex motion, where you might have, you know, skinning of vertices around a skeleton, or multiple objects that are moving at the same time. And we'll look at some examples of that, where we have, you know, planets rotating around a sun, and then a ship rotating around a planet, and so on and so on. Okay. So the hierarchy can get a little complex, but the basic idea is pretty straightforward, right? This program, where we're just tumbling the cube there, it really is just a matter here. You know, everything should look very, very similar. But what's happening is this extra step in here where instead of having a fixed translation and rotation, we are having it vary according to time, and time is in seconds, and so we can deal with this in it's going to continue. We have a nice sine wave, so we're using a periodic function for that. In terms of the translation, it kind of rotates around the screen in a nice way, and then the rotation just is going to continue over the course of time, and wonderfully, since that's a periodic function, that's going to do the right thing as well. All right, so that's all we need to do for animation. So here, every display step, we are changing the rotation and translation, and that is what basically gives us our animation. So all of the animation is really being handled at the CPU level, right? So if we were to look at the shaders here, you'll notice the shaders really don't look any different than our non-animated part, right? Because they are just referring to that uniform variable that is the MV matrix and the projection matrix, which the CPU is changing, right? So we have this coordination going on between the two. So that's why you still need a good GPU, and still need a good CPU, even when you've got a fantastic GPU. Some things are gonna make sense. You know, if it's changing only once per model, like the rotation is only changing once for the whole model, that's why it's happening at the CPU level. Right. Whoops, that's not you, that's Unity. All right. Now, the next step is going to be looking at, well, how would we draw multiple cubes? And this is, again, we get into the situation like there's a million ways to do the same thing. But there is something called instancing. So if you know that you're going to use the exact same set of geometry and the same program and a very similar context for a cube, but you just want to change one thing about that as through multiple instances, you could do it any number of different ways. You could actually do this on the CPU side and call GL draw arrays multiple times. That's one way of doing it. And that might be usually the more common way, because usually you're not using exactly the same model, but say you are using the same model, maybe you're using some sort of particle system, or you're using something where it kind of, you don't have, individual objects. You can replace your GL draw arrays with a function called GL draw arrays instanced. And then you tell it, okay, how many instances of that object or that array, how many instances of that array do you want to draw? So if you had, I guess important thing, if you had the array itself had 36 triangles in it, or 36, whatever, how many triangles or how many cubes, it might have that many things in it. And you say, I want this many instances of that. Everything in that geometry is going to get re-instanced. So you might initially say, well, what's the purpose in that? Because everything is exactly the same. How are you going to render them any differently? What are you going to do? Well, the vertex shader uses, in this case, it would need to use the GL instance ID. Remember, we were able to know the vertex, the index of the vertex that we were using in order when we had the kind of the brain dead version of the vertex shader. So we were able to refer to that index. We can also refer to this instance ID, which will tell us exactly which instance we're drawing. So we'll get instance ID 0 for the 0th one, and then we're going to get instance ID 1 for the second one. So if we wanted to, we could do something like set up a uniform variable that was an offset and say, okay, every time the instance changes, use this offset, and would add that offset to the vertex, perhaps, right? So the example they use is they have the same cube used over and over again with a difference that's calculated based on the index, or excuse me, the instance. And you can modify it, and this is a lot of fun. You can do it with 100,000 cubes, which is pretty darn good. If you have reasonable hardware, it should work. I forget, I had it fill up, it was just a ridiculous number of cubes on this hardware here. Or start with 24 and work your way up. Let's see what state I've left my code in, and we'll get there. Really excited to get to the multiple models one, so let's try to move along. I want to get to that one today. Okay, so for instancing, we're going to run the instancing one. And I have a black frame over there, which is not right. Let me build it just to make sure. Rebuild. There we go. So there's an awful lot of cubes, right? So the rendering of the cube, the geometry of the cube is the same. The only difference is that the vertex shader is effectively handling the animation now, because it is using something for each individual instance of the cube. All right, let's look at that specifically here. All right. We can see that in display, let's make sure I have the right version of display here, yeah. We are telling the rendering program what time it is. So that's one thing that it does. And then it's up to the rendering program to figure out, okay, or the vertex shader then will use the time the instance ID plus a time factor, so they should be basically, as if they were 1 second apart in terms of their animation here. Now at this point it does become the responsibility of the vertex shader to do this calculation, right? So the one downside is that this is going to be potentially, the number of times that you're performing this operation is going to potentially be a lot more than once per cube. It's actually going to be once per vertex, right? So there's sort of a give and take there, right? So now we have this transformation going on, and this math here, even though the rotation and translation might be more or less the same for each cube, or the same for each vertex in a cube, it has to be run multiple times, because there is no, at this level, there's not any particular object level calculation being done. Any questions on that? This one's, I don't know, I haven't personally seen that used a lot, but I can imagine some situations, I certainly haven't seen every possibility when it comes to implementations of things. All right, so it is a trade-off. Still, most GPU hardware can do a pretty good job with all this. All right, so that's instances. Now, this is the one I wanted to look at specifically because I want to contrast the way of doing it with one VAO versus doing it with the way that the book, the plain version of it is. All right, so let's go back to the slides if I can. Okay, rendering multiple different objects. So one way of doing this that you see a lot in a lot of tutorials is that you have a single VAO, you have a single vertex array object, and then you're changing on the fly which vertex buffer you're using with it. Okay, so you have a single vertex array object, a VAO, and then you have multiple VBOs that you're kind of swapping in during the actual rendering process. That happens a lot, right? You see that in a lot of different tutorials. So that's what they're describing here. So you place the vertices for each object in a separate VBO. You can specify as many VBOs as you like. You can have as many buffers. You'll have the geometry associated with each, the attributes associated with each in there, but kind of sitting there latent. Each object will need its own model matrix. The objects will share the same view and projection matrices. So in this case, if you are rendering those two, you're going to need to be changing that every frame because each model does have its own model matrix, right? So that is something that's going to have to change in this as written here. Okay. And then you call GL draw arrays once for each object being drawn. So the scene in the example is a cube and a pyramid. Vertices for the cube are put in VBO 0. And then we have a second VBO, VBO 1, that we use, and the same vertex and fragment shaders can be used for both objects. Let's see. So here's the example code. Let's actually go over to the code, and we'll see how that looks. Go back here. And the normal version with multiple models, I'll say rebuild, just to be sure. And we'll execute it. And sure enough, we wind up with this cube and pyramid. Okay? And looking at the code, it's just exactly as they describe, right? We have a single vertex array object and two vertex buffer objects. And here is the array on the CPU side that's associated with the cube. Here is the array that's associated with the pyramid. And you can see what happens is we have two binding steps. And the binding step, so what is important here is that we're saying, okay, for the following operation, right, we want to say, okay, VBO, that becomes the currently active buffer that we're describing, and we push this data from the CPU over to the GPU. So, okay, that vertex buffer object, which is probably index 0, I would guess, that's what it's going to probably return. So vertex buffer object, this one, is going to have this data pushed into it. And then we change the state so that the current vertex buffer object is now the other one, which is probably index 1, and it's in this array, so it's going to be there. Once we have that associated with it, then we push this data into that one. So we have two vertex buffer objects, and at any particular point in time, only one of them is going to be bound to our VAO, our current VAO, right? So that's why there's one VAO and two VBOs, right? And the binding is really here. This bind up here is just saying, okay, use this VAO right now. So this step here, this GL gen buffers, is sort of independent of that. You could even be generating buffers even before arrays if you wanted to here. So I know I would say it's a common misconception, or at least at one point I had the misconception that this GL gen buffers, somehow these buffers were associated with the current array, which they're not. They are not associated with the current array. No buffer is associated with the current array, vertex array, VAO, until you hit this point here where you actually bind the buffer to the array object. Okay. You don't specify the VAO because it is just the current state, the currently bound VAO. Right? So again, we got to just sort of acknowledge the fact that there's state going on, and we'll wrap this up shortly. All right. So in order to make this work, init is fairly dull. It's setting up our positions and so on, sets up the vertices like we just saw. And then the display program, it says use program, so it is using the set of shaders, and then it sets the MV matrix and the projection matrix, it pushes them to the, well, first it gets the locations from the renderer, from the rendering program, and then it pushes the values to them down here, the uniform matrix. And you'll notice it is doing it every frame. Why? Because it's swapping between the two, because it's swapping between the cube and the pyramid, right? So that here it sets it up for the cube, then it does this, okay, bind the buffer to the array, describe it, make sure it's active, set up your depth tests, then do the render, okay, or at least, you know, queue up that particular piece of the rendering, and then it does the same thing. It's basically now modifying what's in that VAO again with a different set, and it's actually changing what the shader program has as well, right? It's changing the value at MVLoc, changing the values at projection location with these new values that it just potentially calculated. All right. Then it binds that buffer object to the current VAO, makes sure it is described, sets the depth testing, and then draws the triangles associated with the pyramid. Okay, so you have a bunch of stuff going on, even though it's within that one VAO, with that one vertex array object, you're changing the buffers that are associated with that array object in order to render multiple models. Okay, does that, how are we, have I as you try out the examples, it'll make sense. Now, so let's look at, you know, we'll leave some of the other parts for later, maybe for next time, and say, well, how would we do it if we wanted to use multiple vertex array objects, right? So instead of changing the context, or excuse me, instead of changing what the current vertex array object has within it, let's set up two distinct vertex array objects and then just use those over and over again. All right. So, and this isn't covered in the book, but this is the bonus you get here today. So in my code, and feel free to, you know, this can be substituted for one of the exercises, right? If you want to modify your code or do something more with it than I'm doing here, but, you know, so take it and run with it if you want. So here I'm saying, okay, let's have two vertex array objects, and I'm still going to have two vertex buffer objects, one for each of the vertex array objects. All right. Some things are going to look similar, but I am going to set up two renderers just because I want to, two programs. And then I have two sets of positions or indices for my uniform variables as well, okay? Because I have two sets of shaders that I'm going to use, one for the cube, one for the pyramid, just because. The vertex arrays, the initial vertex position arrays are the same, one for the cube, one for the pyramid. And here's where it begins to get considerably different. So, what do? First, I tell OpenGL, yes, I want to generate vertex arrays, and I set up two instead of one. So num VAOs in my case is 2 as opposed to their 1. And then I also set up two buffers, which is what happened before, and that's fine. So I bind the 0th vertex array, so the first one that's set up. I bind the first buffer to that array, so they are hooked together. Then I push the data, that is the vertex positions, the cube's vertex positions, to the currently bound buffer, and I describe it. And I enable that attribute. And I set up also the depth testing for that particular one. So this is all setting up an actual independent VAO, vertex array object. It has a buffer associated with it that has the locations or the vertex attributes in it, right? and then I go ahead and set it up to be used. And here I do it for the second vertex array object, which is just going to have an index. So I set that, I bind that to the current state. Then I say, okay, the array buffer that I'm using with that second vertex array is the one for the pyramid. And I push the pyramid positions, and actually the description is going to be the same. They have the same layout, so their attribute pointer is the same. I have to specify it here because now I'm talking about a different array object. So I did it once up here for this one. I have to, this is setting up, this vertex attribute pointer is setting it up for this new vertex array. Okay. So everything down here is setting up the second vertex array object. So I've got vertex array object 0 and vertex array object 1. In my init program, you'll notice I have two rendering programs, and they vary only by which vertex shader they use. Okay, because I'm going to set color. One set is just going to be solid color, the other one's going to be varying color, so I can tell which is which. I get a location for the MV matrix and the projection matrix for each of those two programs. And then I specifically I calculate a value. So here's calculating the value for the first shader, which has the position of the cube. So the first shader has the position of the cube in it. And the second shader has the position of the pyramid in it. All right. So I did this, I calculated these values. I said which program to use. Program 2 has this set. Program without the 2 is using this set. And now you'll notice my display routine got it a lot simpler. Okay. So all I have to do, and this is one thing now, the program that I'm using, the actual rendering program that I'm using, that is separate from the array object. Okay, the vertex array object, you have to select which rendering program you want to use. You can kind of change them on the fly if you wanted to. That's the one that's not kept with the vertex array object itself. That's independent of that. So you have to say, okay, use this program, and then bind the vertex array and tell it to draw that array. So that's for VAO 0, which happens to use VBO 0. And then the second one, which is the pyramid, I just say, okay, use my other program, which has my other offset in it, and then use VAO 1, which has all the information about the pyramid, and render the pyramid. So the result, make sure to rebuild and run, I didn't break it in the meantime, is that I wind up with my pyramid rendered in this sort of pink or salmon, mauve, I don't know, and my cube, which is rendered in the varying set here. Okay. Now, one neat thing I can do is say, okay, if it's notice it is the rendering program that determines sort of the position and the color here. Right. So if I change the two and I just said, okay, program 2 and program here, what's going to happen is that the cube will now be using program 2. So the cube is drawn at that location with that color, and the pyramid is drawn at the other location with the varying color. All right. So that's a simple way to look at it with, if you want to use vertex array objects independently, you'll be able to set up things, right? So if you had a mesh or you had an object or you had a scene, it is largely a design question. It's going to be about how are you organizing things in your engine, how are you organizing the structure, meshes, and how they rendered and so on. That's going to sort of determine your approach to that. Okay, but it is you think of it. You have a vertex array. So doesn't GL use program load the program onto the GPU? Yes. Isn't data transfer? No. Use program should not. Actually, use program shouldn't be. It's already bound. It's already. If you look in the utils, the prepare and so on, that did the compiling, created the reference. By the time I got down here where everything was bound and attached and finalized, I just then have an index to that program, and I tell it which one to use. Okay. So this process up here is going to be slow. The process of preparing, or potentially slow, preparing, attaching, finalizing, and all that. You don't want to be doing that on the fly. But changing what shader you're using, you can GL use program all you want. That should be as long as it's all arranged and available there, right? So just like the original program, it was switching at every frame for no good reason. So in our case, we're using it for good reason because we have basically sort of a different material and location that's becoming the object there. So, any questions? So just to repeat for those who are watching the stream, the question was, doesn't GL use program load the program onto the GPU, and isn't data transfer between the CPU and GPU comparatively pretty slow? Is there a better way to use the different shaders? And my understanding, my belief, what I've seen in practice is that the once it's loaded, once it's gone through the compilation and attachment phase, and just saying GL use program, that should be very, very little cost, and that's the thing you're typically changing in order to be able to using multiple shaders. Yeah. So any other questions? If not, now's a matter of trying out for yourself. Diving in, even this chapter should go pretty quick. We'll talk. We really just have looking at. Let's see, we did multiple models, so there's the matrix stack. So we'll probably finish up with that next time and start talking about texturing. So we're going to get maybe a little bit ahead. The texturing stuff, the basic texturing stuff is pretty straightforward. I'd have to check the syllabus, but I thought it was, is it 4 through 7? Let's see. That's Game Dev 1. Double checking my syllabi here. I went with 2 of those. 4, 5, and 6. That makes sense, yeah. So 4, 5, and 6, that's going to give us basically, now we've got VBOs, VAOs done properly, the beginnings of texturing, and what do we have in, I'm trying to remember, 6. So we have too many courses. Texture mapping. Oh, yes. This is the trifecta. Yes, the trifecta is using 3D models. So yeah, that's, I should have said before, given 4, 5, and 6, now the world really opens up, right? If you can do geometry the right way, texture it, and potentially even read a model, as you can imagine, that's big. And then everything becomes finesse. At this point, between those 3 things, you basically would have, that's how we did PS1 games. That's how we did Sega Saturn games. We had up to then. It's you should be able to do lots of great stuff with those 3 chapters. So I mean, you're not going to be able to load everything from every model that you could possibly generate, but you should even be able to create some of your own models and things with this next version. So the project should be pretty good. How does that sound? All right. Quick check-ins. All right, we're going to sign off on the streaming if there's no other questions, and I'll try to do quick check-ins just to sanity check and make sure everybody's doing all right.